Hi, in this video, I am going to discuss Cambridge IGCSE Physics Paper 6, May June 2024, Paper 63. Let us get started. Question number 1. A student determines the density of modeling clay by two methods. Method number 1. He uses the block of modeling clay shown in Fig 1.1. Part 1. Measure the dimensions of the block of modeling clay shown in Fig 1.1. Record the values in centimeters to the nearest millimeter. Now, first of all, before you start with recording the dimensions that stated here, like the dimension of length, h, and w, I want you to bear in mind one thing. We are using cm rule to do our measurement, to measure L, to measure H, to measure W. Now, it is very important that you bear this in mind, that whenever you take the reading, you read from cm rule, the one that I'm showing you right now. You have to bear in mind your value, your reading must follow, must be recorded according to the smallest division or the sensitivity of the cm rule that you are using. So the sensitivity or the smallest division of the cm rule that you're using is 0.1 cm, because each scale is gap 0.1 cm. Therefore, all the measurements of L, H, and W must be in one decimal point. This is super duper important. Please bear this in mind. So the L that I measured was 6.2 cm. Just place your ruler horizontally. And W, I got 3.0, one decimal point. H, I got 2.4, one decimal point as well. Now, the third one, calculate the volume VA of the block. Use your measurements from part 1 and the equation VA is equal to L multiplied by W multiplied by H. VA, L is 6.2 multiplies by W, which is 3.0, multiplies by H, which is 2.4. I got 44.6 cm cube. Now, in this case, right, VA is called calculated data because we are using our calculator to do the calculation. That is called calculated data. For calculated data, you have to look at the number of significant figures of the data that you use to calculate. Look at L. L has two significant figures. Look at W. W has two significant figures. Look at H. H has two significant figures. Now, VA can take two significant figures or three significant figures. One more significant figure higher than the significant figures of the raw data. So I'm going to put it in terms of three significant figures, one significant figure higher. So I put it as 44.6 cm cube, or you can denote it as 45 cm cube. It's not a problem. Now B, suggest why the value of VA is only an approximation of the volume of the block. Describe how the accuracy of VA can be improved. I say now, when you look at Fig 1.1, you could see that W, you see a bit crooked here because it is not fixed. The edges are not fixed, right? They don't have like a straight, 100% straight line here. So it is just you approximate the length, the height, as well as the W. So I would say that the ages of L, W, and H varied. So they are not constant. The improvement, I would suggest repeat measurements of L, W, and H along the modeling clay and average. Remember using the word average because you don't just repeat the experiment, you have to find the average in order for a better improvement. C, record the mass MA of the block shown on top pen balance in Fig 1.2. So you just read it off. 80.4 gram is the answer. Calculate a value rho A for the density of the modeling clay. Use your results from A part 2 and C. And the equation rho A is equal to MA over VA. Include the unit for the density. So rho A, mass A, MA, this is the one that I got, 80.4, just read off. 80.4 gram, I just put it gram. VA is the one that I just calculated, 44.6 cm cube. I'm going to put 44.6 cm cube. Now, my rho A, I got 80.4 divided by 44.6, and I got 1.80. I put it in terms of 3 gram per cm cube is the unit of rho A. I put it in terms of 3 significant figures because my mass of A is in terms of 3 significant figures, and my volume, I put it in terms of 3 significant figures. That is why I put 1.80. 1.80 gram per cm cube is the answer. Now, method 2D, the student then uses a small block of modeling clay. It's a block. And record the weight WB of the block of the modeling clay shown in Fig 1.3. Right? WB, you just read it off from the force meter, which is here. Now, this is 0.35 Newton is the answer, 0.35. And E part 1, the student pours water into a measuring cylinder. Record the volume V1 of the water in the measuring cylinder shown in Fig 1.4. So where's my Fig 1.4? This is a 1. So whenever you take the reading from the measuring cylinder, you know that due to the viscosity, right, and then of the water would not form a straight line, horizontal line. So the water will form like a curve like that. That is called meniscus. And then whenever you take the reading from the measuring cylinder, you have to take below that curve, below that meniscus. So this is a reading that you are supposed to take, right? And this reading right here is 42, 44, and 46. Right? So the volume is 56 cm cube. Right? This is 50, 52, 54, and 56. Right? 4 is not my favorite number. Right? Now, the second part, describe briefly how a measuring cylinder is read to obtain a value for the volume of water. I have a lot of idea here. When you want to read from the measuring cylinder, right, you have to make sure that you lower your eye level to where 56 cm cube is. And then you look at the reading below that meniscus. And then your eye must be perpendicular to the scale to avoid parallax error. So I'm going to discuss about that. I say that reading must be taken below meniscus. Okay, I'll give you more than 1 mark because I have a lot of ideas. So you can put 1 point here, reading must be taken below meniscus. And or you can say that the eye position must be perpendicular to the scale on measuring cylinder. Full stop. That's it. F, first part, the student lowers the modeling clay into the water as shown in Fig 1.5. There it goes. Record the new reading, V2 of the measuring cylinder. Now, again, this is below the meniscus. You have to take this reading. This is 70, this is 72, and this is 74. Therefore, V2 is 74 cm cube. Calculate another value, rho B, for the density of modeling clay. Use your value for V2, your readings from D and E part 1, and the equation rho B equals WB multiplies by K divided by V2 minus V1, where K is 100 gram per Newton. Okay, so we're going to do that. Rho B is equal to WB. Remember the one that we recorded just now? I recorded just now. 0.35. Okay, I'll just put in the value. 0.35 and multiplies by 100. Okay, I'll better put in the unit. Okay, for you to see. This is 0.35 Newton multiplies by 100 gram divided by Newton per volume. V2, I got 74 cm cube minus V1, I got 56 cm cube. 56 cm cube. Now, I'll cancel the unit first so that you can see. Can you see Newton and Newton can be cancelled off? So you left 0.35 times 100 gram divided by 74 cm cube minus 56 cm cube. My answer is 1.94 gram per cm cube. This is the unit of density. The 1.94 gram per cm cube. That's it. Now, the second part suggests which of rho A and rho B is likely to be more accurate value. Justify your answer by referring to method 1 and method 2. I would say that rho B is more accurate, right? So I suggest rho B is more accurate. So suggest justify your answer because I said that as the shape of modeling clay is irregular because it is not really a fixed shape, right? And WB, V1, V2 values that being used to calculate rho B are all being measured by apparatus. I'll say that, okay, the shape of modeling clay is irregular. Actually, the one I want to say is because the shape of the modeling clay is irregular. So you make your measurement here, your measurement of L, your measurement of W, and your measurement of H would not be accurate. And due to the inaccuracy of the values of L, W, and H, it will lead to inaccuracy to the volume that you calculated. And at the end of the time, it will give rise to inaccuracy to rho A. Because mass, it doesn't matter because you use the top pen balance to measure it, right? That's the answer. So if you have any suggestion on the answer, please do comment below. I welcome your comment because this is not a fixed answer. Any logical answer can be accepted. So if you have any idea on your suggestion, your justification on the answer, please do comment below, right? Now we move on to the second question. A student investigates how the volume of water affects the rate at which water in a beaker cools. She uses the apparatus shown in Fig 2.1. A, record the room temperature theta R shown on the thermometer in Fig 2.1. Now you see here, this is 10, 11, 12, 13, 14, 15, 16, 17, and this is the one. You have to take your reading here. This is 18. So 18 degrees Celsius. Remember the unit of the temperature. B, the student pours a volume of 200 cm cube of hot water into the beaker and records the temperature theta of the water at time t equals to 0. She records the temperature of the water in the beaker every 30 seconds. She pours the water out and pours a volume of 75 cm cube of hot water into the beaker. The student repeats the temperature measurements for this volume of water. Now, describe two precautions that can be taken to ensure the temperature readings in the experiment are as accurate as possible. I have a lot of ideas as well. I will give you more than two precautions, right? Giving more idea is actually good to help you to answer like more accurately in your coming paper. So I'm going to give you more, right? The first precaution, I say that you need to stir the water. You just pour the water in, right? Water must be stirred. Water must be stirred. Why you want to stir the water? To ensure constant distribution of heat inside the beaker. Don't you think so? Because when you pour the water, you pour like towards the end of the side of the beaker, that part will be hotter if you don't stir it. Don't you think so? Now, the second precaution, I said that, sometimes you don't rush to take the reading. You insert your thermometer, make sure that you wait, you look at the liquid in the thermometer, in glass thermometer, until the liquid in glass, normally is mercury, stops rising. Then only you make sure that you lower your eye level to the scale on the thermometer to take your reading. Right? So I say reading on thermometer is taken once liquid in thermometer stops rising. So you need to give time to the thermometer. You need to give time to the liquid inside the thermometer to expand. And maybe the third one, if you want to add it to it, reading on thermometer meter must be taken perpendicularly. Perpendicularly. So make sure that your eye level is perpendicular to the scale on the thermometer. Or another precaution is that make sure that your bowl of the thermometer doesn't touch the bottom of the beaker. So no touching, right? No contact with the beaker in order for you to ensure that the temperature reading can be taken as accurately as possible. Now, second part, her readings are shown in table 2.1. Add units to the column headings in table 2.1. So I say T measured in second, theta degrees Celsius, and theta degrees Celsius. That's all. C, write a conclusion stating how the volume of water affects the rate of cooling of water. Justify your answer by reference to the result. So justification by reference to the result, you need to give values. So you got to check, okay? This is 200 cm cube of hot water, and the other one is beaker with 75 cm cube of hot water. So you could see that the drop in temperature, I calculated all. So because I want to see the trend, so the drop in temperature is about 2 degrees Celsius here. This one is about 1.5 degrees Celsius. This is about 1.5 degrees Celsius. If you don't want to do all, it doesn't matter. It doesn't matter, right? You can just take one or two reading and compare. That will do, right? So I say this is 1.5, and then the drop here is 1 degree Celsius. So the overall drop from 0 second to 180 second for the beaker with 200 cm cube of hot water is 8.5. Do you know how I get 8.5? I take 87.5 minus 79 degrees Celsius to get 8.5 degrees Celsius. And the overall drop of the temperature of beaker with 75 cm cube of hot water from T equal to 0 second to 180 second is about 18.5 degrees Celsius, quite large, right? So I said that the rate of cooling of a beaker with 75 cm cube of hot water is actually larger, right? It happens faster. So the water, right? The beaker with 75 cm cube of hot water cools down faster at a faster rate as compared to the beaker which you fill in with 200 cm cube of hot water, right? So I say water, okay, oh sorry, beaker with 75 cm cube of hot water, 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 75 cm cube of hot cool at a higher rate or faster rate as compared to beaker with 200 cm cube of hot water. So you need to justify your answer. Why do you say so? Because you need to give the proof, evidence from the result, right? For beaker with 75 cm cube of hot water, the drop in temperature from t equals to 0 second to t equals to 180 second is 8.5 degrees Celsius, whereas beaker with 200 cm cube of hot water, the drop, better write it nicely, okay, the drop in temperature from t equals 0 second to t equals 180 second is 18.5 degrees Celsius. Now, D part 1, using the values of 475 cm cube of water, calculate the average cooling rate, X1. For the first 90 seconds of the experiment, use the readings from table 2.1 and the equation x1 is equal to theta 0 minus theta 90 divided by t, where t is equal to 90 seconds and theta 0 and theta 90 are the temperatures at t equal to 0 and t equal to 90 seconds. Include the unit for the cooling rate. Now I'm going to do it. X1 is actually equal to theta 0 for 75 cm cube. So I'm going to look at here. Theta 0 is 85.5. So we have to be extra careful with this kind of question. 85.5 minus theta, which is when it is at 90 degrees, which is 75, minus 75 divided by t is equal to 90. So I just put 90 here. Now I got 0.117. How do I get the unit? You know theta, the unit of theta is degrees Celsius, and the t is in second, degrees Celsius per second. Therefore, the unit is degrees Celsius per second. 0.117 degrees Celsius per second is the unit of for the cooling rate. Now, using the values for 75 cm cube of water, calculate the average cooling rate, X2, for the last 90 seconds of the experiment. Use the readings from table 2.1 and the equation X2 equals theta 90 minus theta 180 divided by t, where t is 90 seconds. Theta 90 and theta 180 are the temperatures at t equals to 90 seconds and t equals to 180 seconds. It is still 75 cm cube, right? Water. So X2, be careful. Theta 90 is 75 degrees Celsius and theta 180 is 67. Focus on 75 cm cube of water, yeah? 67 divided by 90. I got 0.089 degrees Celsius per second. 0.089 degrees Celsius per second. Third part, a student states that it is important to start 2 experiments in B with water at the same initial temperature. Explain whether your values for X1 and X2 support this statement. I said that, okay, I'll give you the value of X1. X1 is equal to 0.117 degrees Celsius per second. X2, the reading is 0.089 degrees Celsius per second. So the difference between the 2x value or delta x is equal to 0.117 degrees Celsius per second minus 0.089 degrees Celsius per second. I got, right, is equal to 0.028 degrees Celsius per second. I would say that the difference in x value, or I put it in words, the difference, okay, in x1 and x2 values are, I would say, quite large, quite large, which is beyond limit of experimental accuracy. That is why I put 3 dot, right? This one, okay, because the students state that it is important to start the 2 experiments, right? That is why I have to support this statement. Yes, you have to start with the same initial value, because if you don't start with the same initial temperature, then the difference will be quite large, right? So that is why statement is supported. Oh, I spell it statement. Large statement is supported. So for this part of the question, right, actually there is no right and there's no wrong answer. So if your result is quite small, right, you think that 0.028 degrees Celsius per second is small. So the way you answer it is that the difference in x1 and x2 values are quite small, which is still within the limit of experimental accuracy. So that is why you don't support the statement, right? So there is no fixed answer here. It is based on your own judgment. Now, E, another student repeats the experiment. State 2 variables other than initial water temperature that he should control to obtain readings that are as close as possible to those in table 2.1. I say that, hey, this experiment is being conducted, in room temperature, right? And then there is no lid to cover the top of a beaker. That is why I have to make sure that the surroundings temperature must be constant. And I need to make sure that the same amount of volume of water, right? So that the experiment, right, the result could be as accurate as possible. And then you need to make sure that the size of the beaker, or you can say size of the beakers, right? Or third one, you can say size of beaker. Make sure that they're of the same size, right? Now, the third question, number 3, a student determines the focal length of a converging lens. A, the student set out the apparatus as shown in Fig 3.1. He sets the distance due between the illuminated object and the lens to 25 cm. He places the screen near the lens and moves the screen until a focus image of the illuminated object is seen on the screen. Describe a technique for obtaining an image that is as sharp as possible. Actually, it's very hard to determine the sharpest image, because due to the experiment that is not being conducted in a dark room, right? And then due to the light from this light bulb illuminated object being absorbed by some other materials nearby, being scattered. So that is why the image form is a bit blurred, right? So, but I will discuss a technique, right, that we can use to obtain, even though it's a little bit blurred, but as sharp as possible, right? So first one, I will just say that move the screen back and forth, back and forth, forward, backward, right? And then where the sharpest image is obtained, because you don't know initially, until you see, okay, when you move forward, no, quite blurred, then try to move backward a bit. Oh, I found it. That is the sharpest image. Right. Okay, I stop right there. And then once you determine, oh, that is the sharpest image, then you move screen a little forward and a little backward to confirm the sharpest image. Is that okay? When you have already determined the feeling of excitement, right? You try your best to move just a little bit forward. Oh, blur. Just move a little bit backward. Oh, blur. Oh, so that's the sharpest image. That is how you confirm that's the sharpest image. Right? B, the shapes of the illuminated object and the image seen on the screen are shown full size in Fig 3.2 and Fig 3.3. Now, the first part, measure h naught, the height of the illuminated object, as shown in Fig 3.2. Use your ruler to measure again. I got 2.0 cm. Remember what I told you at the start of the video? I said that since we are using our cm rule, all the reading, all the measurements that we made, right, h1 and hi here, must be recorded in 1 decimal point. Do you still remember why? Because the sensitivity or the smallest division of our cm rule is 1 decimal point, right? That's a reminder. I got 3.2 cm. And then calculate a value, W, using your measurements from B part 1 and the equation W equals H naught, which is 2.0 divided by H I image 3.2. My W, I got 0.63. No unit for W, 0.63. C, the student repeats the procedure for U equals to 20 cm, 30 cm, 40 cm, 50 cm, and 60 cm. His results are shown in table 3.1. Plot a graph of U. U must be on the y-axis against W. W must be on the x-axis. Use the results from table 3.1. You do not need to start your axis at the origin. So you can start with any other value. Draw the line of best fit. I actually draw smaller. I actually start from origin. But if you don't want to start from origin, maybe your y-axis, you can start from 10, 20, 30, 40, 50, and 60. Not a problem, right? So this is a graph, and I plot all the points here. D part 1, determine the gradient G of the line. Show clearly on the graph how you obtain the necessary information. So when they ask you to show clearly on the graph, you need to draw the right angle triangle, and you need to state your 2 points that you use to calculate your gradient. Right? So I have already shown here. G, I am supposed to calculate my G. Remember, G can be calculated from y2 minus y1 over x2 minus x1. This is a little bit of math here. So the G is 64 minus 16. 64 minus 16 divided by 3.15 divide minus 0.2. 3.15 minus 0.2. Okay, let me do it for a while. 64 minus 16 divide 3.15 minus 0.2, and I got 16.3. 16.3 is my value, 16.3. Now the third, the focal length f of the lens is numerically equal to the gradient. Record a value for of f for this experiment. So f is equal to gradient. That is why f is equal to 16.3, right? So 16.3 cm is the value of f. E, a student decides to continue the experiment using a larger values of U. Explain why this procedure produces less accurate values for W. Now I have to look at the connection between W and U. I will just use this. W is equal to H object over HI. So now W is equal to H object over HI. Now, based on the graph, right, you could see that when the value of W is increasing, the value of U is also increasing, right? or the value of U is increasing, the value of W will also increase, right? So when the value of, because they say that using larger value of U. So I will say that from graph, right? I will explain here first before I write down the answer, right? Or I could also write down the answer from graph. Okay, I would say that when U increases, W increases linearly. Okay, or you just say increases, it doesn't matter. And W depends on H object over H image. When W is larger, H image will be very small, right? Because W is inversely proportional to H image, right? Therefore, hence, it will be very hard to measure HI since the value will be super duper small. So that is why, yeah, less accurate values for W, because at the end of the time, W is calculated from H object and HI, right? So I welcome you. If you have any suggestion for the answer for part E, please feel free to comment, right? Now, the last part. Question number 4. A student investigates the relationship between the diameter of a wire and the electrical resistance of the wire. Plan an experiment which enables her to investigate diameter of the wire affects the resistance of the wire. Resistance R can be calculated from the equation R is equal to V over I. That is why you are not supposed to use ohm meter as one of your apparatus, where V is the potential difference, PD, across the wire, and I is the current in the wire. The apparatus available includes wires of different known diameters, and in your plan, list any additional apparatus needed, which I'm going to do it right now, or before that, complete Fig 4.1 to show a circuit suitable for measuring the resistance of a wire. Okay, you know what? When a resistant wire, do you know what is a resistant wire? Resistant wire is the wire without insulator. It is like a piece of metal, like that, very thin metal, right? Maybe copper, maybe zinc, maybe constantan, right? So the wire is not straight naturally, right? Therefore, right, in order to measure the resistant wire, so I have to make sure because this is relationship between diameter of the wire and the resistance, right? So the length of the wire must be constant. How do I make sure that the length is constant? I make sure that I cut the wire of equal sizes. So I place the wire, I tape it on top of my meter rule. So I place the meter rule right here because I want to make sure that during the experiment, the length of the wire is always the same. Easier. I don't have to take out the wire and measure it again and again, right? That's it. And then I put an emitter here. Emitter must be connected in series with the power supply. So it could be beside the power supply, left-hand side or right-hand side, it doesn't matter. Don't worry. And then here, because this is a resistant wire, I want to make sure that the resistant wire is not being overheated because we are investigating the diameter. Maybe the diameter, some of the diameter I use or the students use will be small to like burn the wire, overheated the wire. That is why, as a safety precaution, I put something else here, which I call it as variable resistor. And remember, resistant wire, you want to calculate the resistance of the wire, you just connect this to N because a voltmeter must be connected in parallel. And don't just leave your diagram like that. You have to label your diagram. This is ammeter. This is meter rule. Resistor wire has already been labeled, so I just leave it there. This is variable resistor. And this is my voltmeter. So I have completed the second part first, which is Fig 4.1. Now I'm going to list additional apparatus needed. Okay, so I'm going to put here additional apparatus. So I put variable resistor because I want to control the amount of current. I don't want my wire to be melted. Resistor. I put ammeter. I put a voltmeter. I need that. As well as meter rule because I just want to make sure that the length of the wire must be constant throughout the whole experiment. And the third one, explain briefly how to do the experiment, including the measurements to take so that the resistance can be determined. Okay, I'm going to do it now. That is under methods. So first of all, be polite, set up the apparatus as shown in Fig 4.1. Length of the wire. Length of wire is measured by meter rule. And then length. Okay, I will suggest here. Suggested is 100 cm. Easier. So just use the full length of the meter rule. And then I say diameter of the wire. Diameter of wire is measured by micrometer screw gauge. And then after that, I say that switch on the power supply. Power supply is switch on to 1 volt. I just use a small voltage. And the readings on ammeter. Okay, I put this at I, and voltmeter. I put this as volt are taken. Done. And then after that, resistance is calculated by equation R is equal to V over I, capital V. And then don't just stop there because the final point, right, for the method must be repetition. Experiment is repeated with different diameters of wire. Done. So I put a tick here first. I'm done. Okay, state the key variables to keep constant. There's so many things to keep constant here. I call it as controlled variable, sorry, plural, right? So I said that I want to control the temperature of the wire. That is why I put in the rheostat temperature of wire, length of wire, and the voltage of power supplied, right? As long as you write more than one, you are safe because that's plural. You have to write more than one. And the next one, draw table or tables with column headings to show how you display your reading, right? So table, this is my table. So I write diameter first. Meter of wire, which is in mm. And then ammeter reading, which is in ampere. And then voltmeter reading, which is in volt, and then resistance, which is in ohm. Right now, just draw a line like this will do. Okay, make sure that the volt must be capital. And I'm done with table. And the last part, explain how to use the readings to reach a conclusion. To use the reading to reach a conclusion, I will say that conclusion, plot a graph of diameter against resistance to see the relationship. So that is all about May June 2024 paper 63. If you have any suggestions on how the experiment could be planned, I welcome you. Most welcome to comment below. Thank you very much for watching. Right? See you in my next video. Bye.